your virtual pages in the physical memory at the same time? No. You just need the pages you're working on actually. So you only, if your program runs in forward and back in 10 pages, then 10 pages is all you need to allocate in the physical memory, even if your program are several hundred pages. Meaning that with a limited physical memory, you can run more programs in parallel because of the virtual memory than you would be able to otherwise. So you only need those pages which are active in each program, so you can have more programs running on the computer. You're young, so you don't remember the old versions of Windows where only one program could run, and if you tried to run more programs, which you actually could, the programs very often broke because they couldn't coexist in memory. That's not an issue today. Yes. So the degree of multi-programming can be increased. Actually, we have worked on how many programs are finishing, doing the work they should, and out here we have the number of programs running. And if we run if we run those programs, no work is done, and if we run one program only at a time, then one program is finishing when or the work done by that program is proportional to the program. So we have a curve something like this, and then at some point it breaks because here we have started too many programs to run efficiently on our computer. So what happens here when the system breaks?
Have to swap the program.
Yeah, so the programs, because we have limited physical memory, so when all pages in the physical memory are used up and we want to fetch a new virtual page, we have to get rid of one of the pages in physical memory before we can get the new page. So we have to write a virtual page, we have to write a physical page to the disk before we map a new virtual page into that area. So if we do that all the time because we have used up old space, then we do a lot of swapping instead of doing practical work. So this is called the thrashing point of the computer. And there's only one way to handle that, and that is killing some of the programs you have started, and doing that you will go back on the curve, and at some point you will have a system which is running. You have seen that a lot of times. You very often see this program is not responding. That can be different reasons, but it could be that it takes too long for the program to have physical memory allocated. So it seems as if the program is actually not working. So haven't you seen that a lot of times? This program is not responding. Do you want to kill it, or do you want to wait? Because in some cases, waiting will actually, the program will eventually be run, but in many cases you will have to wait for a long time. So in most cases, I think, kill it. Then as we go back on the curve and have a system which become responsive once again. Yes. So, and then also we talked about virtual memory offering shared memory and offering possibilities of doing map files. Those are the other important services. So, okay with that?
I have a question.
Yeah.
I don't quite understand how segmentation fits in with virtual.
Oh.
I mean, I understand, but
Yeah, it's true because the Intel processor is they're basically born as computers using segmentation.
does Linux, for example, only segment is the different stack area?
I think the Intel processor has two ways of running. It can run what we call linear memory, or it can run what we call segmented memory. And I think in most cases, Unix-like systems are running linear memory. They are not using the segmented memory. It may be that newer versions of Linux are actually running segmented memory because you get a protection scheme using segmented memory, which you do not have when you're running linear memory. So to get that protection, newer versions of Linux might use segmented memory. I suggest that you do not touch upon it's not that it's difficult, because an address here is a page number and an offset. So the page number and an offset. And if you have a segmented memory, every location is in a segment. And segment can be big. And because segments can be big, you divide segments in a number of pages. So now you give the segment number, and within the segment you give the page number, and within the page you give an offset. So this uses a page table, this one uses a segment table, and for every segment in the segment table, you have a page table as well. So every segment has an associated page table, except for small segments. Small segments are not divided into pages. So things get a little bit tricky when we're talking about it, because we have to differentiate between big segments and small segments. Big segments are divided into pages. Small segments can be as small as 1 byte, so they are not divided into pages. And we have those two kinds of segment tables: big segment tables and small segment tables. And it's indicated in the entry if it's a big segment table, or if it's a big segment or small segment, and if it's a big segment, it points to. So there are two levels of indication. So segmented memory would run slower than linear memory, and running virtual memory using page table is of course slower than running than programs running on the physical memory, because we have to go through a level of translation before we can access memory. So this translation takes a number of clock cycles, right? And if you had one more level of indirections, you would use even more clock cycles. So. And I think if we look at the most common computers nowadays, the ARM processors and things like that, they have linear memory. They do not use segmented memory. So I think that the Intel processor is probably the only one using segmented memory. So don't worry too much. Being this part is important, and knowing that using virtual memory you can also offer shared memory, and and because you have a huge virtual memory available, you can map your files or part of your files into virtual memory and access files as if they were arrays, rather than reading data and writing data on the disk. That's the important services. Okay, true or false? The use of virtual memory makes every computer instruction slower. True or false? True, because we are going through a translation which requires a number of clock cycles. The CPU issues physical address to the address bus. True or false?
The operating system doesn't use pages, does it?
The operating system doesn't use pages. Okay, you remember the illustration I gave at some point? having the CPU issuing a virtual address and then a MMU, which is doing the translation. So now you get a physical address. So you have to pass the MMU to have a physical address. So I would say that the CPU issues virtual addresses to the MMU. That is true. Then again, you can have the CPU running in at least two modes. It can run in kernel mode or it can run in user mode. If it's running in user mode, these are virtual addresses. If it's running in kernel mode, these are interpreted as physical memory. So you are a bit right. The address bus can run both kinds of addresses, but only when it's in kernel mode. This will be seen as an address which is not going to be translated. And the reason for that, of course, is that we want the kernel to be common to all processes. So this is the kernel memory.